Hello and welcome to this video showing how to analyze 4G or LTE signals with the IDA 2 from Narda. We're located in Germany, in Europe, where we have a few digital or DVB-T signals in the lower frequency area. We can also see a few LTE signals right here, around 800 megahertz, and of course we can also see GSM 900 here. Our start frequency amounts to 450 megahertz. Our stop frequency is amounting to 1 gigahertz, and at the moment we have a resolution bandwidth that is 300 kilohertz. The video filter is still switched off, and in order to enhance the view onto all of these signals, I typically prefer to just activate a slight video filtering. Therefore, I'm clicking on bandwidth. Once again, I am choosing BBW video bandwidth and set it to 1/10 of the RBW, and once activated you will see in the spectrum trace that it starts smoothing, and by that we have some sort of averaging and can sometimes see signals simply better. In order to increase the sensitivity, we can also decrease the RBW from 300 kilohertz down to 100 kilohertz, and based on this setting now we can step by step focus on the LTE channels of interest, which are right here. So for focusing on those channels here, I now activate the spectrogram marker. I move the marker onto the center of those channels, so it was already set there. I simply move it there once more, and I push marker to center in order to adjust the center frequency. Based on this setting, I can now simply decrease the span setting. Right now we still have f-start, f-stop as frequency parameters. In order to change that to f-send, f-span, we simply push f-start twice, and now we can change f-span from 550 megahertz down to, let's say, 40 megahertz. Well, and as there's just one significantly strong LTE channel on air and the other one is rather weak, we should maybe focus on that strong one only. Once again, I want to make sure that I have the correct frequency adjusted. So once again, I make use of the marker, spectrogram marker or spectrum marker, doesn't matter at the moment. And then I move in there, adjust by marker to center. So now again, the center frequency has been changed. I'll leave the marker menu by pressing escape. And once again, I decrease the span to, let's say, 13 megahertz. Right now, our spectrum trace is still a little coarse. So in order to enhance that view also, let me decrease the bandwidth, the resolution bandwidth, down to 30 kilohertz. And by that we can already see pretty well that there is quite something going on in spectrum. So we can see that the power, the overall power is fluctuating definitely, and we can also see that sometimes it's just specific portions or very thin, narrow portions within that signal being activated and deactivated once again, and correspondingly we can also see that in the spectrogram and the waterfall, sometimes there are, well, like on a heat map, more active zones or more active portions and less active portions. So we will get into this in detail later on when using not the usual spectrogram but the IDA's high resolution spectrogram. But first, let me try to work only on those pulses in time domain. So the current view that we see, the spectrogram, is one view that the IDA provides. Another one is now also the time domain scope mode, and we can go to that mode by simply clicking on extras and time domain scope. When using that extras go to function, we can make sure that the center frequency stays the same. And moreover, when changing from the spectrum to the time domain scope mode, we also have to make sure that the corresponding or that the channel bandwidth is correctly set. So what we have to make sure is that we cover with our channel all the power that was of interest in that LTE band. So the bandwidth of LTE typically amounts, in this case now, in this area, to 10 megahertz. As a consequence, also in time domain scope mode, we need to set a channel bandwidth of 10 megahertz. So as we're in time domain scope, as mentioned, on the x-axis we have ranging a scaling in milliseconds. So this is now just like an oscilloscope, and we could also enhance or increase this view based on 2 milliseconds up to 20 milliseconds. So that we see a higher time span, and that we can also see how the signal evolves in that period of time. Well, as we want to focus only, or as I only want to focus on those very short time slots, let me decrease the span again, the time span, to 2 milliseconds. And let me try to capture one of those moments where we can see those very short time slots, simply by clicking hold. And we can of course try that several times until we have found a convenient moment, such as this one here. And now we try to measure the duration of these time slots here. Of course we could try to read that, but in order to find out about that duration in detail, we simply make use of the markers by pressing marker. And now we have two markers in charge. We can see that by that marker function delta BA. Of course we could also change to a single marker, but what we want to do now is change to marker delta BA. And we move now marker A, which is now active, to one slope of those slots. Typically I want to get just the edge, like this one here. And now I change to mark B and move it to the other slope. And based on this, we will try to find out the duration of one of those pulses here. Okay, I think this is fine. Up there in the top of the screen, you can now see the timestamps and the field strength values for the markers. What I'm actually interested in is the time difference between those two markers, and this is now 0.000067, so roughly 67 or 70 microseconds. So this is now the duration in here. And those ones of you who have a little bit experience with LTE or LTE standardization might expect a value of 71 microseconds. So this is the real value that we should expect in here when correctly setting up the markers. Because 71 microseconds, according to the standard, is the minimum time duration depicting one time slot, specifically and precisely one time slot. And we will come to that later on, again in the IQ analyzer, where we can see the resource grid, and where we can again see in the resource grid how one time slot is taking 71 microseconds. So this is how we can analyze LTE now in the time domain scope mode. Based on that setting, I want to leave the marker menu again, and I want to go back to the spectrum. Because what I'm showing next is how we can analyze the signal in the IQ analyzer, where we provide a sophisticated, high-resolution spectrogram. And the main difference between this spectrogram and the spectrogram that we will see right now is that the data are not, well, continuously being presented, but they are first captured and then processed in a sophisticated way so that we can see very, very deeply into the signal. So now the spectrum, the spectrogram, the waterfall is ranging, it's scaled up in the range, in the time range of a few seconds. And once we now go to extras and go to the IQ analyzer, it's first a huge amount of data that is being captured, processed, and afterwards displayed like this. And this is now going on and on. Of course, it's taking a while from measurement to measurement. One can say that within that time frame, we have a gapless, very reliable measuring. And this is now what we call the high resolution spectrogram in the IQ analyzer operating mode. And in the high resolution spectrogram, we have different subviews, which we can access right here. So when clicking on view, we can also display the same data in the high resolution spectrogram Zoom, which we will use right now. But just to make that aware again, right now the spectrogram amounts not anymore in the range of seconds, but actually in the range of milliseconds. And we get a spectrum trace, a spectrum line, each 9.6 microseconds. So comparing that to the sweep time that we had earlier in the range of 10 or 20 milliseconds, now we get a spectrum line much quicker. Actually, we have improved by the factor of roughly 1000 or 2000. So depending on the settings you have chosen, this factor, this improvement of time resolution can vary somewhere between 500 and 2,000, sometimes even 4,000. Okay, and well, basically we see now also, let me just go back to clarify that, what we saw here in the range of seconds, and where we could see those heat zones, those more and less occupied portions in the band, comparing that to this view in the IQ analyzer, we now understand what is actually going on. So now we see very precisely that there are distinct signals or portions in that band that are being switched on and off, and all of this is changing continuously. So depending on the traffic that has to be transmitted around us, of course there are more frequencies in that band being used, and sometimes it's less. Right now, the IDA captures a time span of 18.75 milliseconds in order to process the data. What we can also do, we can go and hold for one measurement, and we can reprocess all that and zoom in more or less. So right now, all of those 18.75 milliseconds are being displayed at once. We can also go to the high resolution spectrogram Zoom, so that the same amount of data is being reprocessed and displayed. And now, in a smaller scale, we can start scrolling down and see very precisely when, where a specific portion in the band is being used, or more used or less used. We would also be able to see, especially during the phases when the signal is being switched off, whether there is any interfering influence, whether there is maybe an illegal transmitter just aside of our band. So with the help of that high resolution spectrogram, we're able to see very deeply into LTE actually, and we can now reveal the so-called LTE resource grid, consisting of radio frames, subframes, time slots, resource blocks, and so on. So those terms come up typically when you're dealing in detail with LTE standardization. And we're now just going back to the high resolution spectrogram full view and just have the IDA running for a couple of moments. We can now see that all of that is changing continuously. So obviously none of the signals stays the same. All of that is traffic changing here and there, but actually there is one component that stays the same very regularly, which is always right here in the center of our band. So this is the so-called PSS, the primary synchronization signal. It's got a bandwidth of precisely 1 megahertz. So you can see right here on the x-axis, this is 2 megahertz. In the middle, this would be 1 megahertz. So this here is just the span of 1 megahertz. And those PSS signals typically appear in a period of 5 milliseconds. Right here, right here, right here, and so on. Sometimes we might also be able to detect some other PSS signals from other base stations, from other E-node Bs, as LTE is a single frequency network technology, meaning in the same band from the same operator, we might also receive other base stations, other E-node Bs. So what we're now focusing on are those stronger ones, but sometimes, such as here maybe, or here, you might also be able to detect smaller or weaker PSS signals. Let's just wait for a moment where there is not so much data to be transmitted, and then stop the measurement again to see in detail, to take a closer look on those PSS signals in the high-resolution spectrogram Zoom. So right now I go on hold, and now I can change to Zoom. We now see we have a PSS signal here and here. This is a time difference of 10 milliseconds. Of course, we might have one here in between, which is more or less interfered by some traffic. Well, but what we can do now is we go on Zoom again, and now we start zooming in and take a look at all those PSS signals. So there is one right here, and another one is to be expected 5 milliseconds later, so roughly around 13 milliseconds. Probably right here where we can see some slight gaps, some slight dips. And another one is to be expected at 18 milliseconds. So this is that one here. Well, and these are the so-called PSS signals. Earlier in the time domain scope mode, we were also mentioning time slots taking 71 microseconds. So this is one other thing that we can now work up on, simply by measuring the shortest signals that we can see in this area here, and the shortest signals that we can see time-wisely are those ones covering the entire band. So those ones are actually reference signals, or they are also abbreviated by RS in different books, in various literature. So what we are going to do now is we go on Marker and try to measure the time duration of those reference signals. Therefore, we have to make sure that we once again activate both markers. So now we have delta time and frequency, meaning we can navigate over both time and frequency with both markers. And initially, I would now like to navigate over time with one marker, with active marker A. So let's take active marker A in this area here. You can also see that depending on the position, on the time position of the marker, the corresponding spectrum up here changes. So right now we don't see anything in the spectrum yet, anything specific. And once I move the marker up in this area, of course I will also correspondingly see the spectrum popping up. So let me find a useful moment for marker A, and then go to marker B and also navigate over time so that I can move it down just to the other slope of the same time slot. So now it's still disappearing, and now I go up again and see how the spectrum is popping up. Right, and depending on where I set the marker, but it's already obvious, of course I will see something around 71 microseconds up here for the time difference of both markers to each other. And this once again confirms the duration of one time slot, officially 71 microseconds, in this case now 76, 77 microseconds, with help of a visual setup of the markers. Right. Let's continue our nice measurement here, And let's focus on the last feature that we can very nicely reveal with help of the IDA. Therefore, we have to focus on one specific portion in the band. We simply have to drastically reduce the bandwidth. So I'm now still watching the entire LTE channel, and what I'm doing next is I decrease the bandwidth to the channel bandwidth to 2 megahertz. The displayed span will be 1.6 megahertz. And then we can start on working on the technology that is actually behind LTE. I'm referring to OFDM. OFDM means that in your band you have many carriers that are very close to each other, that are spaced to each other in very small steps in a very specific way, and each of that carrier, in order to transmit data, is being modulated if needed. And when now zooming into the LTE band, as we just did, we're already able to see some straight lines here, which is at least a hint. It's actually not all of the carriers that we had expected, but it's at least a hint on those carriers. And I want to find now just a calm moment where we don't have so many data to be transmitted, but just nothing in fact. So as you can see, those straight lines, they're obviously active all the time. In fact, they are not 100%, but we will come to that. So let me find a moment when there is no data transmitted, such as this one moment now. Oh, that's not so good yet. So this one might be convenient. And now let's try to measure the distance or the spacing between the carriers that we can see here. And what is now important is that we have to differentiate between adjacent carriers that we can obviously see. So first, let's take the markers and navigate over time to find moments where there's obviously less data to be transmitted and where we can only see those carriers. And I think just this area here looks pretty unnoisy, pretty convenient. So let's move one marker in this area here, marker B, and also let's get marker A down there. So this is where marker B is, and I want to set marker A just to the same moment, or to the similar area, more or less. And right now we can see that not only in the spectrogram we have those straight lines, those carriers, but also we see the corresponding carriers up here in the spectrum. And what is also pretty obvious, that those carriers they change in a way. So let me just try to indicate that by moving the marker from the top to the bottom. We can now see that there is a carrier here and there is one here. But once I start moving the marker down, it's just changing. So we still have the same spacing from here to here, but this carrier, which was supposed to be earlier, disappears, also that one that we saw here, and we have just a shift. So now it's those ones that are active. And once I start again moving the marker down, it's now again this area and this area that is active. So obviously we have a continuous change of active carriers in a very short amount of time. So once it is that spacing that is in charge, and depending on where I move the marker, it's just the adjacent one. So what is important now for the next measurement, for the frequency distance measurement that I'm heading to, is to correctly set those markers A and B at identical timestamps, so that you will definitely have a moment where you have identical markers or identical carriers in charge, and not just the different or the opposite ones. So I have now marker A at 16702 milliseconds, and I'm just putting marker B to the same timestamp. So I'm comparing those values here, and now I can, without any problems, move my two markers frequency-wisely to one and another carrier, which I can see here. And what I get now is a frequency distance amounting to roughly 90 kilohertz. And 90 kilohertz might be another buzzword for you if you're familiar with the LTE standard, because what we thought earlier, or what we assumed earlier, is almost true. So of course those carriers that we can see here, they are the real carriers that are being modulated in case of traffic to be transmitted. Right now in this case, when we speak of a frequency distancing of 90 kilohertz, it is just every sixth carrier that is in charge. So normally LTE carriers are being spaced in 15 kilohertz steps, and as we now have a frequency spacing of 90 kilohertz, this is a clear indication that it's only every sixth carrier that is being modulated. And of course this is pretty obvious, so of course sometimes we also have those traffic phases which look much denser compared to those straight lines. So by that we see that there must be carriers in between that are only active when there is actually data to be transmitted. So this is now a very complicated feature, and you have to be familiar a little bit with the LTE standard to reveal and to understand what you're actually measuring. But basically, with help of the IDA and its markers and the IQ analyzer, there are some very neat tools in order to analyze LTE in detail and also to check whether there are any interferences in between. Okay, so that's it so far. Please let me know in case you have any other interesting issues or questions on LTE or other signals. And thanks for watching this.